All right, well, once we get to this point, now if you notice, I already have my f of xy. It's just that I'm not finished yet because I still need to find what g of x is. Then I would have the complete f of xy. All right, well, let's see how we can do it. Now, if you recall, we used the second condition from partials to find the actual f of xy. Now, as I said, the only thing left for me to do is to find g of x. Is there anyhow I could use the other condition to help me find g of x? And it looks like we can, because it says if you took the partial of f, whatever f is, in this case, this happens to be f. So if it says if you take the partial of that with respect to x, which is x squared, and I'm just going to multiply this out, minus y, and I don't even need to put the parentheses anymore, plus g of x. Now, if I took the partial of that with respect to x, it tells me that the result should equal 2xy. Well, if I took the derivative of this with respect to x, the derivative of x squared y will be 2xy. The derivative of y with respect to x will be 0. And the derivative of g of x with respect to x will just be g prime of x. Aha. So if you recall, we used to have stuff like this in algebra. Now all you have to do is equate coefficients. 2xy goes away. I have g prime of x equal to 0. And if I integrate both sides, that tells me that my g of x is equal to a constant, because the integral of 0 is a constant. Take the derivative of a constant, you get 0. So now I have a value for my g of x, which happens, it's a constant. So now I can write my function, my f of xy, x squared minus 1y plus a constant. But that's not my solution. Remember, my solution is when f of xy is equal to a constant, that's f of xy. So the actual solution is, you see, it's kind of weird, because if you wrote this, it wouldn't be the solution, that's just the function. The solution would be f of xy, which is x squared minus 1y plus a constant, equals to a constant. And you call the constant 1 constant 2, so you can call this x squared minus 1y is equal to a constant, because c2 minus c1 is just another c. And actually I'm lucky here, because I actually produce an explicit solution here, and the explicit solution would simply be y equals c divided by x squared minus 1. And there is my solution to this exact differential equation. I'm going to do one more example. Let's look at the second example, which is e to the 2y minus y cosine of xy dx plus 2x e to the 2y minus x cosine of xy plus 2y dy equal to 0. Now this is a bit more interesting, and it's probably going to be a bit more interesting to find derivatives and integrals here, but the process still remains the same. All right, so let's start with labeling m and n. So m of xy is here, and this is n of xy. So my m is e to the 2y minus y cosine of xy, and my n of xy is 2x e to the 2y minus x cosine of xy plus 2y. Now, recall that I need to first satisfy the exactness criteria, so I need to show that partial of m with respect to y is equal to partial of n with respect to x. So I'll take the derivative with respect to y of e to the 2y minus y cosine of xy, and that must be equal the partial of n with respect to x, which is the derivative of 2x e to the 2y minus x cosine of xy plus 2y with respect to x. Now, if I took the partial of partial of m with respect to y, let's see what will I get. The first one will be the derivative of e to the 2y, which is 2e to the 2y. minus, now the derivative of this function with respect to y is a product rule. So it'll be first times the derivative of the second with respect to y, so it'll be minus sine of xy times the derivative of xy with respect to y, which is x, plus cosine of xy times the derivative of y, which is 1. So that's the derivative of my left-hand side. Now I can clean this up to e to the 2y plus y sine of xy. Actually, it's xy sine of xy, right? Because minus and a minus gives you a plus, and then you have a y, you have an x, and you have a sine of xy gives you that product. Plus, actually, minus times the plus would be minus cosine of xy, because you got a plus here, but you have a minus here that multiplies the brackets, turns that into a minus. So that becomes the derivative for me for taking the partial of m with respect to y. Now let's take partial of this one, n with respect to x, and hope that we get this. Because if you do, then I have satisfied the exactness criteria. Well, let's see. Partial of this with respect to x will be, let's start. So let me actually just make a copy of it and write it down here. So I'm trying to find that partial. So look at the first one. The derivative of that with respect to x is just 2e to the 2y minus, now the derivative of this is again a product rule, so it'll be first times the derivative of the second, but this time with respect to x, so here will be y plus the second times the derivative of x with respect to x, which is 1, plus the derivative of 2y with respect to x, which is 0. So if I clean this up, 2e to the 2y plus xy sine of xy minus cosine of xy, I can clearly see that these two are the same. So therefore, I have satisfied the exact criteria, and therefore I have a green light to go ahead with this. All right, so let's go back here. I'm going to erase this, and I'm going to start so you could actually see the equation when I'm doing it, and you guys could always rewind the video and copy this. So I'm just going to delete all this because I don't need it anymore, because I already verified that it's exact. Alright, so now, yeah, that's clean. Alright, so now, and let me get rid of these m's because I don't need them anymore. Great. Alright, so now recall, now that I've gotten the green light to solve this, recall, and I'm going to do this again, that z is equal to f of xy is equal to a constant. Taking the total differential of that will produce dz is equal to partial of f with respect to x dx. First partial of f with respect to y dy is equal to 0. And that looks exactly like the differential equation I have. So very clearly from here I could see that partial of f with respect to x is equal to e to the 2y minus y cosine of xy. And partial of f with respect to y, I can see it's equal to that. So it'll just be 2x e to the 2y minus x cosine of xy plus 2y. So these are my two partials that I already know. And our objective here is to find f of xy. Okay, so let's start with partial of f with respect to x and integrate both sides. So you have to start with one of these. So I'm going to start with the first one, looks easier. So partial of f with respect to x is equal to e to the 2y minus y cosine of xy. Because again, you're going to have to find that f of xy from one of these. But there's no other way to do it. So I went with the easier one. Now let's integrate both sides. obviously with respect to dx. Left hand side gives me what I'm looking for, and I need to integrate the right hand side. Now the integral of, I'm going to actually write this out, the integral of e to the 2y dx minus y is a constant, I pull it out, the integral of cosine of xy dx. So it just breaks down into that. Now the integral of e to the 2y dx is just x e to the 2y. And the y is a constant, so it just sits there. And the integral of cosine of xy is 1 over y sine of xy, right? Excellent. So this becomes minus, and that constant 1 over y with the y cancels out. You could easily integrate that yourself, and you end up with sine of xy plus, since my integration with respect to x, my constant is going to be a function of y. If my integration was with respect to y, my constant would have been a function of x. So this is the solution so far. However, I'm not done, because A, I need to find g of y, and B, I need to take f of x and set it equal to a constant, and that will be my final solution. And again, just like the previous example, how are you going to find g of y? Well, you're going to go to that equation that you didn't touch. So you touch number 1. You work with number 1, you got to f of x. To find a constant, you have to work with the other one. So I know from the other one, the partial of f with respect to y. I know from this one, that partial of f with respect to y is all this. But I have f of xy now. So all I have to do is take the partial of this with respect to y. So I take partial of this thing with respect to y and set it equal to that thing, and that's how I will find g of y. Let's actually do it. So I'm going to take the partial of f with respect to y, so I'm going to take partial of all this and that has to equal this. So that has to equal 2x e to the 2y minus x cosine of xy plus 2y. It has to equal that. Well, let's see. Taking the derivative of the first one, x is a constant, comes out. Derivative of e to the 2y is 2e to the 2y, so it's 2x e to the 2y minus, now the derivative of sine of xy with respect to y is cosine of xy, and since I'm differentiating with respect to y, x is a constant, so I get x cosine of xy, plus the derivative of g of y with respect to y is just g prime of y, and that has to, again, equal to this. Now you notice, with a smile, that you got terms that are crossing out, and it should always work that way, because it doesn't, then you've made it as some kind of a computational error, and ultimately you end up with g prime of y is equal to 2y. Now that's simple, you just integrate both sides with respect to y, so you get g of y is equal to 2y squared over 2, which is just y squared. So now I'm ready to write my function first. F of xy is equal to x e to the 2y minus sine of xy plus y squared. That's my function. That is not my solution. This is f of xy, but it's not my solution. If you give this to me as a solution, that's a technical error. The actual solution to this equation is written as just the f of x, not f of x symbolically itself, but what it actually is. Because the solution is, I'm going to write it here, is f of xy equal to a constant, not just f of xy. So it's f of xy equals to a constant, and that is the solution.